Welcome to this module, where we explore power evacuation and grid connectivity for solar PV systems. As renewable energy becomes a major part of global power generation, grids are evolving, from simple, centralized networks to dynamic systems connecting multiple solar and wind sources. In this session, you'll learn how power flows from PV plants to substations, the key equipment involved, and how smart grid protection and connectivity standards ensure safe and reliable operation. Join us to understand how solar power integrates into the grid, shaping a resilient and sustainable energy future. Solar panels convert sunlight into electricity through the photovoltaic effect, where photons from sunlight strike semiconductor materials, like silicon, in the solar cells, releasing electrons. This flow of freed electrons creates a direct current DC electric flow, which is then typically converted to alternating current, AC, by an inverter to power homes and appliances. Proper switchgear and substations ensure efficient power evacuation. This equipment is critical for ensuring the efficient evacuation of power from a large-scale solar power plant to the electrical grid. They perform essential functions like voltage transformation, grid synchronization, power quality management, and system protection, which are vital for a reliable connection as follows. Role of substations in efficient power evacuation. Substations serve as the backbone connecting a solar farm to the broader transmission network. For large-scale projects, which can be hundreds of megawatts, substations are indispensable for integrating massive and variable power generation into the grid. Voltage transformation. Solar panels generate low-voltage direct current, DC power. The inverters convert this into low or medium-voltage alternating current, AC. Substations then use large transformers to step up this voltage to high-level transmission voltages. This is necessary to minimize transmission losses over long distances between the remote solar farm and population centers. Grid synchronization. The substation is responsible for matching the solar plant's voltage and frequency with that of the utility grid. This seamless synchronization prevents disruptions and maintains the stability of the larger electrical network. Reactive power compensation. Solar plants can affect the grid's reactive power balance, which is necessary for voltage stability. Substations are equipped with devices like capacitors and reactors to regulate this, preventing voltage fluctuations and reducing transmission losses. Functions of switchgear in efficient power evacuation. Switchgear is a combination of electrical components, switches, fuses, and circuit breakers, used to control, protect, and isolate electrical equipment. Within the substation, it provides the control and protection necessary for reliable and safe operation. Switchgear automatically detects and isolates faults, such as short circuits or overcurrents, from the rest of the electrical system. By preventing these disturbances from spreading, it protects both the solar equipment and the integrity of the grid. Flexible distribution and control. Switchgear allows operators to manage the flow of electricity efficiently. In large solar plants, it can be used for sectioning the medium-voltage MV system to minimize power outages during maintenance. Advanced systems offer remote switching capabilities, giving grid operators better control over power flows. For maintenance and repairs, switchgear allows specific sections of the solar plant to be safely isolated from the grid. This allows maintenance personnel to work without shutting down the entire plant, saving time and improving overall efficiency. To maximize efficiency, the design of the switchgear and substation must address several challenges unique to large-scale solar power. Handling variable generation. Solar energy output fluctuates with sunlight, which creates an intermittent power supply. Properly designed substations use advanced controls to manage these variations and maintain grid stability. Grid code compliance. Large solar plants must adhere to strict grid codes regarding power quality, voltage, and frequency variations. The substation design incorporates features like fault ride-through (FRT) capabilities and reactive power control to meet these regulatory requirements and avoid operational penalties. Environmental resilience. Many large solar farms are in remote locations with harsh environmental conditions like high temperatures, dust, and wind, like in India and Rajasthan. Robust, weatherproof switchgear and substation enclosures are engineered to withstand these elements and ensure reliable, long-term operation. Smart and digital integration. Newer technologies, such as digital and modular substations, reduce installation time and land use while allowing for real-time monitoring and advanced automation. Integration with SCADA, supervisory control and data acquisition systems, gives operators better visibility and control, further optimizing performance. Energy storage integration. As battery energy storage systems, BESS, become more common, substations are increasingly designed to accommodate them. BESS can store excess solar power generated during the day and discharge it later, helping to stabilize output and reduce stress on the grid. A single-line diagram, or SLD, is a simplified representation of an electrical power system. It shows the flow of power from the generation source to the grid, highlighting all major components like transformers, breakers, and meters. It shows power flowing from solar panels, DC, to inverters, AC, then through transformers and a switchyard before being transmitted to the electrical grid. Key components include the PV array, DC combiners, inverters, transformers, and switchyard, which then connects to the utility grid. Simplified symbolic layout of electrical connections. A simplified symbolic layout of the electrical connections for a large-scale photovoltaic PV system shows the flow of energy from the sun to the power grid, highlighting the major components and the conversion process. PV array, DC combiner box, inverter, step-up transformer, substation, utility grid. Essential approvals for large-scale solar plant grid connectivity in India for illustration include the following. DISCOM NOC, a fundamental mandatory requirement to confirm the grid has the capacity to absorb the power generated. State Load Dispatch Center, required for synchronization with the grid and ensuring the plant complies with state-level solar policies and grid stability requirements, such as active power control and reactive power support. Chief Electrical Inspector, CEIG, a mandatory safety and electrical standards compliance check that is critical before commissioning to ensure the electrical systems meet all safety norms. CTU and STU coordination, necessary for transmission and evacuation planning to ensure efficient power transfer from the plant to the grid. Metering arrangement confirmation. Confirmation is needed on the type of meter, for example ABT meter, to be used for measurement and billing at the point of connection. Technical compliance. The plant's technical specifications, such as reactive power control capabilities, for example, from 0.95 lagging to 0.95 leading power factor, must meet the grid code requirements. Environmental clearance, required for large-scale projects to assess and mitigate their environmental impact, often from the State Pollution Control Board. Land use conversion. If the land is agricultural, it needs to be converted to non-agricultural use. Forest Department clearance may be required depending on the project's location. Fire Safety Certificate. A certificate from the local fire department is necessary for safety compliance. This includes cable sizes, protections, and metering systems. Let's look at the stages in the power evacuation process from the PV array all the way to the grid. DC generation in PV arrays. Combiner boxes for protection and cable management. Inverters convert DC to AC. Step-up transformers increase voltage levels. HT switchgear monitors and protects high-voltage systems. Transmission lines carry power to the substation. Meters record energy flow at grid interconnection points. The evacuation system ensures the safe and efficient transfer of power from the PV plant to the grid. Switchgear, circuit breakers, disconnectors, relays, substation, transformers, metering, control rooms, transmission lines, route selection, conductor type, and tower design. Protections, overcurrent, ground fault, reverse flow, anti-islanding, and voltage regulation. A large solar power plant, say of 5 megawatts capacity, includes specialized equipment to manage power evacuation. 33/11ths of a kilovolt switchyard, ring main units, RMUs, HT/lieutenant panels, transformers, power/control cables, earthing, safety gear, lighting, testing, commissioning, and regulatory approvals. Integrating large-scale renewable energy introduces challenges such as intermittency, voltage control, and transmission constraints. Let's explore these and their solutions. Challenges. intermittency and variability of renewables, grid stability and frequency fluctuations, mismatch between generation and demand, transmission from remote locations, storage and backup requirements, mitigation, advanced forecasting and grid automation, energy storage and flexible generation, smart grid technologies and demand response, upgraded transmission infrastructure, market reforms for renewable integration. As renewable energy continues to expand, effective grid integration is essential for large solar power plants to ensure a stable and reliable power supply, maximize the use of generated energy, and integrate the intermittent nature of solar power into the overall electricity network. It allows excess energy to be sent to the grid, provides power from the grid when solar output is low, like at night, and reduces the need for expensive on-site battery storage. Through robust planning, smart infrastructure, and advanced technologies, solar power can be seamlessly integrated into modern grids. Thanks for going through and reading. Don't forget to like, share, and subscribe for more solar insights from I-SED Academy. Please go to I-SED Academy platform for detailed learning about solar technologies.